So for the rest of Chapter 9, we're really going to be talking about the physical properties of solutions. So I'm on page 19, and I've got these concentrations. I've got, that's methanol, CH3OH, 1 mole per liter. If I were to think about the solute particles, I'd say, well, there's 1 mole per liter. And you're thinking, so what? Well, here's vitamin C, 1.60 moles per liter. I have 1.60 moles per liter of particles in solution. Ammonia. That's a teeny bit of a fib, but it's pretty good. Ammonia, that's 0.50 moles per liter. I've got 0.50 moles per liter in solution. And you think, okay, Wallace, I don't know what you're doing. You're just saying, yeah, there's the concentration, and you're writing down the concentration over here without really thinking about what the particles are. You're just saying, well, yeah, it was 1 mole, 1.6, 0.5 moles per liter. So what? So lithium chloride, 1 mole per liter. When I look at the particles in solution, of course, I have 2. Well, wait a minute. Okay. Potassium sulfate, 1 mole per liter. Well, it's got to be just 1. All right, well, what about this sodium phosphate, 0.2 moles per liter? It's just got to be 0.2. And it's 0.80. So what's going on with those things? Well, let's go back and think about this. When I put this CH3OH in water, it dissolves. It dissolves really nicely. When I put sugar in water, we know C6H8O6 aqueous. When I put lithium chloride in water, I get lithium ion aqueous plus chloride ion aqueous. Notice what I'm getting. I'm getting like 2 for 1. Stop the video and figure out how sodium phosphate would break up compared to those numbers. All right, you did it, right? You said, oh, I remember from chapter 3 and chapter 5, this would be 3 sodium ions plus 1 phosphate ion. I'm getting 4 for 1. Well, these are electrolytes. Strong electrolytes, in fact. But what strong electrolytes do, or what all electrolytes do, first of all, they dissolve in water. But they break up into ions. Break up into ions. Now, this means a couple of things. The concentration of the ions, the moles per liter of ions, is greater than what's on the label. In other words, I had lithium chloride, 1 mole per liter, but the concentration of ions was actually 2. And so what's really in the bottle, the concentration of the stuff that's interesting to us, concentration really equals the concentration of the ions. And this is, again, I just want to remind us, we're talking about electrolytes. So electrolytes. Now, there's another really important property of electrolytes, but I'm going to have you stop right here. I've got these 2 videos in the Canvas assignment, so watch those, and then we'll come back and pick up page 19 at the beginning of page 20. So, since we're talking about this new situation where the molarity or the concentration inside the solution really is not the same as what the label says, we have to come up with a new term. So we had said molarity is moles of solute per liters of solution. Now we have this thing osmolarity, which is moles of all particles. So we can take a solution and just say, I don't care if it's ions, molecules, atoms, add everything up. Well, this becomes very important for strong electrolytes especially. So here I've got 0.67 moles of magnesium chloride. Now I recognize that as soluble, and it's a strong electrolyte. It's a soluble ionic compound. So I have to remember when I put magnesium chloride solid in the presence of water, I get magnesium ions plus 2 chloride ions. Remember, this is where chapter 3 is coming back to haunt us if I don't recognize it. Oh yeah, chloride doesn't stay together as 2. Chloride breaks up. Those are 2 individual things. So I might do this like this. 0.67 moles of magnesium chloride. And I want to get to total moles of ions. Moles of ions. That's what I'm trying to get to. I can say, okay, moles ions, moles MgCl2. Well, I'm getting 3 for 1. 3 for 1. Stop the video if that doesn't make sense. Think about that. That gives me 2.0 moles of ions total. Now let's calculate the osmolarity. Osmolarity always sounds like it'd be an excellent name for a heavy metal rock band. I have to recognize, oh yeah, that's a strong electrolyte. In water, I'm going to have K plus aqueous and bromide aqueous. So I'm getting 2 ions for every 1 mole of KBr. So I could formally do this. I could say, okay, 0.35 moles KBr per liter times 2 moles ions, 1 mole KBr equals 0.70 osmolarity. I think sometimes that gets shortened to OSMOL. Here's a trickier one. Glucose. We said sugars like that are non-electrolytes. They dissolve in water quite nicely, but 0.15 moles per liter of glucose is 0.15 moles per liter particles. Here, however, what am I going to multiply that by? Stop the video and figure out, okay, wait, am I going to multiply this by like 7 or 2 or what? Stop the video, you figured out, oh, I'm getting 3. I'm getting 2 potassiums and 1 sulfate. Remember chapter 3? So I'm going to multiply that by 3. So I could say, oh, my osmolarity 0.15 plus 0.050 times 3 gives me 0.30 osmolarity. Again, if that doesn't make sense, stop. Think about that. How to get the 3? Why did I break that up? What did I need to know from chapter 3? Now, in a medical situation, here I'm telling you everything I don't know about blood and that biology stuff. But so I guess there's blood, which is a solution, and there are blood cells, which must be these little spherical things sort of floating around in there. So when the osmolarity of the blood is equal to the osmolarity inside the cell, we say it's isotonic. And the blood cells are happy for reasons that we're going to see later. If the osmolarity of the blood sort of around the blood cells, we say this is hypertonic. And for reasons that we'll see later, the blood cells are unhappy. It can be destructive. If the osmolarity of the blood around the blood cells is less than what the osmolarity is inside the blood cells, we say that's hypotonic. Again, it's not good for the blood cells. And we're going to talk about that the next three pages in lectures. We're going to talk about properties of solutions.